All right. So welcome to the day 5 stream of me working on my game engine. Um, when we last left off, I was working on some asynchronous resource loading. But over the weekend, I tried to continue working on it and ran into some really weird bugs. And it looked like it could have been an error with the Rust code generation. So it was seriously like I was digging down at the assembly level and some weird stuff was going on. So I tried updating the Rust compiler and I wound up running into some other weird errors that I only just managed to get resolved like last night as I was going to bed. So let me take a quick detour and show you something interesting that was going on. So I used to be doing this. So this is within Bootstrap GL. This is the function for Windows that, given the name of an OpenGL proc, loads the pointer to that proc. Specifically, we call wiggle get proc address. We pass it a C string, so that has to be a null terminated ANSI byte string. And given that your OpenGL context is set up correctly and you pass it the name to a valid string, it'll return you a valid pointer. And now I've had a bunch of problems with this in the past. Weird things where sometimes it would return null even though it seems like I've got the OpenGL context set up correctly and all of that. And I've mostly worked around it, but there's still stuff going on that I don't fully understand. So when something breaks related to this, I'm like immediately wary. And so this is what I was doing originally when I was trying to load the string. I used the CString class within the standard library. What the CString class does is, given a Rust string, Rust strings are UTF-8 non-null terminated. They carry their length with them. You give CString a Rust string, and it will allocate a buffer, copy in the valid ANSI, and then append a null terminating character. So now you've got a C compatible string. And then I would get a pointer to that string by doing string.unwrap.asPointer, and I would pass that pointer into wiggle get proc address. And this worked fine. This was code that I wrote a long time ago, maybe like a year ago at this point, where I wrote the initial version of this code, and it apparently has not changed much since then. But it worked. I was doing this. I would pass in the pointer, and I would get out the right proc address, and that was all hunky dory. Just the other day, I updated to the latest Rust Nightly, wondering if it would fix the other bug that I was seeing within my code, and this stopped working. Wiggle get proc address always returned null, which was very confusing to me. And I was looking at this, and I was like, I don't understand what's going on. And so I tried breaking this up again. I tried doing like let cstring pointer equals cstring.asPointer, and then doing this. I believe I specifically did this so that I could like see what cstring was. And much to my surprise, suddenly it started working again. And so I went on the Rust. The only thing I could think of happening was like, oh, something changed with the way that destructors were being run. Because what I could tell was this was written before I really understood Rust. So cstring new returns a result, probably. Either a result or an option, probably a result. And it'll return an error if it fails to convert it to a C string. Like, so if you have some characters in this string that can't be represented in like an ANSI string, it has to be represented like Unicode only characters. This will fail because you just can't convert it into a C string. And I didn't fully understand that at the time. So I put the unwrap here just because Rust said, oh, you got to unwrap it before you can take the pointer to it. And so what I didn't realize was happening was the actual C-string object is being returned from unwrap. And I'm not, what I was expecting is I was expecting this to be the C-string object, and then I take a pointer to it, and I can pass the pointer in, and since I've got this binding named string, I was expecting that the destructor won't be run until string goes out of scope here. What I didn't realize was happening is string is actually option C-string. And so when I unwrap is what is returning the C-string. And then I do as pointer on the return C-string, but I never bind the actual C-string to a variable. So right after as pointer is called, the C-string gets dropped. And so now this C-stir binding no longer points to valid memory. And so that code is what I've had for a long time, and that code has always been wrong. But interestingly enough, it never failed. It just it always ran just fine. The C code doesn't care because hell, C code is used to dangling pointers all the time. So I was really confused. I was like, what is going on when this started failing? And so I asked around on the Rust forums. I thought there might have been something weird with how, something changed with destructors. Maybe the C-string destructor was being run at a different time. Maybe it used to be accidental. Maybe there was a soundness error and it used to be running here even though it should have been running up there or something. And when I went and asked on the forums, somebody pointed out to me that there was actually a recent change to C-string so that it would zero out its buffer when it's dropped, specifically to catch bugs exactly like this. And so what do you know? They caught my bug. So I thought that was pretty interesting. I thought that was interesting that the Rust developers, somebody figured that somebody would be having this issue and made a change to help me figure it out. So that's the frustrating thing that I was dealing with over the weekend. But now I've got that figured out. I know Rust a little bit better, so I can tell what was going on. That's also not terribly important at this point. So, woo. What is important is the other thing that I was working on over the weekend. So when we last left off, I believe I had started working on mesh loading, but I had gotten about this far. I'd gotten to the point where I had about this much. I could load text from file, I could load the mesh data. And then what I originally had was in my engine, I had a mutex around the renderer. So instead of a box render, I had a mutex box renderer. And then this code would be doing something like, engine.renderer.lock, .unwrap, .register mesh data. It'd be doing that sort of thing. We had to lock the mutex in order to register the mesh. And I was saying, that seems less than ideal, because now I've got a point of synchronization across all my multiple threads. And let's say I've got 1,000 meshes that are loading in all at once. I would like to be able to not have to have all of those different threads serialized, stop running in parallel in order to get my meshes loaded. Worse than that, loading a mesh and loading a material would also have to happen in serial instead of in parallel, because they would both require locking the mutex on the renderer. So if I'm loading 100 meshes and 100 or 1,000 meshes, 1,000 materials, 1,000 textures, potentially any other thing that we've got to send to the renderer, we lose all the benefits of parallelism. So I was thinking about it, and I was thinking how could we fix that? And the solution was to use, or the solution I came up with, I don't know if this is necessarily ideal, but the solution I came up with was to use a channel. And this is what I was talking about doing on the last stream, and then I got impatient over the weekend and started working on it and ran into a bunch of problems that hopefully we won't have to deal with today, but who knows, maybe I'm going to be spending most of today's stream debugging assembly. That'll be fun. That'll not be fun. So what I've done now is the engine has a render message channel. We create this when we create the render. So we create the render, then we create a channel. We get a sender and a receiver. Each of the worker threads that we spawn at startup gets a clone of the sender, and that clone goes into thread local storage. If we take a look here, we have a thread local variable called render message channel, which is effectively a sender that sends this render resource message type into across threads. When we create the worker thread, we set up that thread local variable. We just overwrite that uninitialized initial value, and then we kick each thread off. Now, this sending and making it a thread local variable is a minor optimization that I did for my own convenience. The way that my multi-threading system works is I kick off, some number of threads, and for the time being, I've made that value configurable. So right now I'm specifying we've got 4 worker threads running, and so there'll be 4 worker threads. But at any given time, there could be hundreds, thousands of units of work in the form of these fibers that and if I wanted to if I didn't want to use thread local storage, I'd have to make them local to the fibers somehow, which is potentially even more difficult because there is no Rust standard library support for fiber local storage. I'd have to invent that myself, which is complicated. Plus, I'd have to have substantially more clones of this sender, whereas I know there's only going to be at most one piece of code trying to send a render message per worker thread. So just having one sender per worker thread will probably, one, it's easier for me to initialize at startup. 2, it's potentially faster. It's more convenient. Because I imagine there's probably some synchronization that happens when you clone the sender, clone and drop them, because there's probably a reference count inside between the senders and the receivers. So that probably has to be updated. So the sender goes to the worker thread, the receiver goes into the engine, and then what we do is within the engine's main loop, I've also started to rewrite the main loop. This is where the main loop is defined currently. It will probably move someplace else, but it's convenient to just put it here now. And you'll notice I do the run macro, so this is actually being run on a worker thread. What we do is we're going to do some updating, but there's no updating to do now. We're going to do some drawing. But after we've updated, but before we draw, what we're going to do is we try to pull out all the messages pending in the channel, and any pending messages will get sent to the GPU and get set up. And what we've done is I've added some. Now this potentially poses a problem. So what used to be happening was load mesh was returning that GPU mesh. So when I register a mesh with the renderer returns a unique ID for that mesh that just represents that mesh, the data of that mesh stored on the GPU. It's completely opaque. You can't read from it or write to it, but you can use it to fetch that data and tell the renderer which mesh you're referring to. Load mesh used to return that directly. Back when I was doing, in here I was doing engine.renderer.lock.register mesh. I had that GPU mesh identifier, and I could then just do GPU mesh. That's no longer the case. At the time that this code gets run, we no longer have access to that GPU mesh. So the way that I've had to work around that is now the engine also generates unique IDs for the meshes. And the way that we're doing that is actually with these atomic values. I have this mesh ID counter, which is a static atomic use size that starts at 1. And each time we create a new mesh, we just add 1 to the value, and that's our new ID. This allows, using this static atomic allows me to potentially have many different mesh loads happening in parallel, and I know that these IDs that are being generated are always consistent across all threads, which is terrific because the whole point is to make this multi-threaded. I wouldn't want to be using some non-thread safe version that's going to cause problems. So now we generate an ID, and this ID is basically a lazy value. It's referring to a mesh that doesn't yet exist, which is actually an issue that I have not resolved yet. And I'll talk about that kind of as we get there. But so what we do is we send a message to the renderer, basically to the engine, to pass in turn to the renderer. And we say, hey, I've got a new mesh that I want to give this ID, and it has this data. Whenever you're ready, take your time, no rush, but whenever you're ready, get this data sent to the renderer and get it all sorted out. And then before the next time the engine will draw, it does just that. It takes that mesh ID and the mesh data, it registers the mesh data, and then it will have to do something. This is the part that I have not yet gotten to because I ran into problems with doing the same thing with the material. And we will see if those problems still exist or not. But, to do somehow associate mesh ID with GPU mesh for future use in rendering. So that's the thing that I still have to figure out. And then I can do effectively the same thing with materials. However, I've got something to be careful about. Let's do a thing. Let's discard some changes. Discard some changes. That I have to keep. Let's discard some changes. Discard some changes. And what we're going to do is git stash pop. Will that break anything? Here, your local changes to Windows mod.rs is going to break things. Okay, I'm going to discard those changes, but I don't see that working. Git stash pop. Alright, so what happened now? So now we have discard those changes. So now if we take a look at resource.mod, we can see that I've done it for both meshes and materials. So we take a look at resource.mod. We got load mesh and load material that's doing this render message channel. And you can see there's also a bunch of junk within render message channel, and that is because I was having a bunch of problems with it. But we are going to test that out and see what happened. We're going to see if I'm still having those same problems. I'm also going to run to the bathroom quickly and get another thing of tea brewing. Ooh. Oh, damn it. Okay. Sorry for that delay. So let's see what we're looking at. What? Sorry about that. I managed to let my tea go cold, and that is not ideal. I like iced tea. I do not like cold tea. So that error that we saw just now, GL enable pointer for GL enable is null, unable to load proc pointer. That's exactly the issue I was just talking about, and I forgot to reapply the fix. So let's go ahead and do that quickly. Windows mod, and then inside load proc, I put the unwrap at the wrong spot. Let's go ahead and do that again. I'm going to cross my fingers, but I don't have a ton of super high hopes. If we start running into that bug that I was dealing with over the weekend, the one where well, we'll see. Suffice to say, I was trying to debug it for a while, and I don't know what was going on. It is, oh geez. Well, all right, folks. Get pumped, get excited, because it's debug o'clock. I mean, it'll be fun. It'll be fun to take a look at the debugger, what's going on. Unhandled exception. Access violation reading, executing some location. So here's a thing. Jump fiber platform fiber proc. $2F ED5CH. 2F ED. Oh, 2F ED5C. Jump to the next line. Okay. Alloc box bool call once. Alloc heap box free. Huh. So let's stop this, cancel, and let's start digging in, and we can see what's going on. Solution Explorer. First things I gotta do, gotta change the working directory in Visual Studio so that it actually runs properly. Next thing I gotta do, I gotta open up my Gunship source async resource mod so that I can actually place a breakpoint, load material, let result equal channel send, then we hit run. and we run to this breakpoint. And if I hit F10 to try to step over it once, we get our error. Also note that the access violation is at a completely different address than it was last time. Last time the address almost looked like it could be a valid address in memory. 04C, not a valid address in memory. So we hit break, and it seems to be telling us that the issue is here. I don't know what this means. I'm not sure what's going on. So this is actually, within my fiber library, this is when you spawn a fiber in using the Win32 API, you pass it a pointer to a function that it executes on startup, and that's what this is doing. It's Win32 is calling this from the new fiber, and it's passing in just like a pointer. You give it a pointer to any data, and it will pass that pointer back to you once it kicks off the proc. In our case, that pointer is a pointer to the function that is going to be run. So I cast it back to the right type and then invoke the function. That seems to be working. I'm not 100% sure what's going on though. What matters is if we restart this, we gotta open up the disassembly. Okay, let's split this view up. So we are currently here. We had a couple of calls. We had a call to memcopy right here, but we don't really care about memcopy. What we do care about is this call to send, which is actually what we're calling here. So we're going to run to that, and then we're going to hit F11 to step into it. So now we're at the top of send, sender send, and if we take a look at ESP, this is our stack pointer. For those, if you are familiar with assembly, what ESP is this is actually a register on your CPU. I believe it's on the CPU. I actually don't understand it well enough, but this is a register. And this points to the top of the stack. And what's important is, if we step up our call stack a little bit, the last assembly instruction that we executed was call. And what call does is it pushes an address onto memory, specifically this address, the address of the next instruction, and then it jumps to the address specified as the argument. So it jumps to the entry point of the send function, which is at this address. And if we go to where it jumped to, this is the address that it specified, I believe, OC09320, OC09320, and we take a look at ESP, which is the stack pointer. If we tell Visual Studio to interpret this as not a void star, as a void star, actually as a void star star, because ESP is a pointer to another value, we'll see that the value that it points to, OOC2F906, the next address that we want to return to is OOC2F906. So this is what's important. We know that at this address in memory, at 0632 F714, at this address in memory, we can actually take a look in the memory window. Boop, drop that in. Let's interpret this as a 4-byte integer. Give it one column. We'll see that at this address in memory we have OOC2 F906. So that is exactly what we want. We want at the start of the function, we want our stack pointer to be pointing at the return address, and we want that return address to be the correct return address. And if I do this void star star, we see currently that ESP is this value, and that's good. That's the way we want to do. If we now start stepping through this function, it calls an inner send message. That's interesting. I don't know what's going on there. We keep walking. It's doing some junk, doing some junk, doing some junk. Calls memcopy, doing some junk, doing some junk. Calls memcopy again. Then it does something with an inner value that's unsafe. No surprises there. Then it jumps to another address. Then it does some things. And here we are. This is the part that's important. The return instruction. So the return instruction is the opposite of the call instruction. Call pushes the return address onto the stack and then jumps to the specified address. Return pops the address off the top of the stack. It treats the 4 bytes at the top of the stack as being as a pointer to memory, and then it jumps to that address in memory. So if we step to the ret instruction, we will see what we should expect to see is ESP should have the exact same value it had before, and that value should still be that address in memory should still contain tripping over my own words a ton. That address in memory should have the same data. Like nothing should have written to that address in memory, because if it did, then it's corrupting the stack, and that is going to cause problems. If we take a look, that address in memory is unchanged. Nobody has overwritten it. It still has the return address. We're still good to go. But before we execute the ret instruction, if we take a look at ESP, we'll see that ESP has a different value. ESP is supposed to be 0632 F714. It is instead 0632 EFB8. That is not right. Somehow, within the body of the sender send, the stack got messed up. Something is not right. Wait a second. Oh wait, OCH. OCH. That value is familiar to me in a way that makes me uncomfortable. Alright, so let's take a look. Visual Studio is a little bit nifty in that you can just kind of punch in values and it'll be nice to you. Oh, 075C. Huh. I could have sworn OCH was the value that it was off by before, which would indicate something. Yeah, that's so if I take the difference between the expected value and the actual value, we find that it's off by a couple hundred bytes. Actually, this might be a couple of kilobytes. I have no idea what's going on. This seems like nonsense to me. So I've run into an error like this before. I've run into an error where I noticed that the stack, it wasn't that the stack was getting corrupted, but somehow by the time a function got to the ret instruction, the return address the stack wasn't in the right state. The stack was somehow like getting in an inconsistent state. And what I found was happening was I was using Rust's FFI capabilities, but I was using the wrong calling convention. Specifically, the case was with my OpenGL stuff. Let's see. It was in this glproc macro. It was pub function, pub mod. proc pointer, proc type, extern system. So what I was doing was, instead of extern system, I was doing extern C, which works fine for most cases. It works fine on most platforms, except on 32-bit Windows. Windows expects you to use the standard calling convention, and I wasn't. I was using the C calling convention, which behaves slightly differently, specifically with regards to how it pushes and pops values onto the stack when you call into and when you're exiting a function. And because the calling function and the callee were using different calling conventions, it left the stack in a slightly invalid state that was causing the value at the top of the stack when it got to the ret instruction to just be some random value, and so my function was jumping into invalid memory on return, which was just a huge pain in the ass to debug, but eventually I figured it out. In this case, I've since fixed that. I now know that the correct calling convention is system in this case, because this will either pick C or standard call, whether or not you're on 32-bit Windows, which is kind of a weird little edge case, but solves my problem. What I don't understand is channel send is not an FFI function. It's not something that I declared. It's not a C function. It's a Rust function. It's not an unsafe function to call. It's safe. I mean, I'm doing some unsafe stuff here because I have to do this. I have to, wrap it in an unsafe cell. But actually wonder if I could get rid of wrapping it in an unsafe cell, but I will not worry about that just a second. As far as I can tell, what I'm doing around here is right. At the point where it calls into the function, everything is hunky-dory. And it's like, without any outside intervention, solely within the bounds of this function, things start to get weird, which is just very confusing. And so when I started working on this over the weekend, I thought this was a code gen bug. Like, I thought Rust was something was causing Rust to spit out bad assembly, like bad machine code. And I mean, I'm still not sure if that's the case or not. It seems unlikely. Like, I expect code gen bugs to be pretty exceedingly rare within Rust. I am using the nightly compiler, but I don't know. This does pose a conundrum because I have an okay understanding of assembly and all of its strangeness and inner workings. I don't understand it well enough to, step through this entire function, because you saw how many instructions there were. Oh my god, why would the disassembly window not stay open? Let's pin this motherfucker. So we run to here. We F11. We've seen how many steps there are in here. This is pretty long, and each of these instructions is potentially, pushing values and popping them onto the stack. Actually, that's not true. Move doesn't push things onto or off of the stack. Leah doesn't. The only thing that does would be call. Sub wouldn't. Jump wouldn't. Add wouldn't. So just pop. So there's actually only a couple of places where this corruption could be happening. So I think I'm going to debug it. I think I'm going to step through this function, keep track of what's going on with the stack pointer and find out where things start going wrong. And this might be incredibly boring to stream, but I think I'm going to find it incredibly interesting. And I'm either going to uncover a bug in the Rust compiler, or I'm going to learn something very interesting about what I'm doing wrong here. Either way, that promises to be fruitful. I'm going to continue to do this for another probably less than half an hour. I'll probably I'll try to get as much of this done as I can off stream. And I'll hopefully just be able to share the results on stream, because God, I can't imagine stepping through disassembly is going to be great. What I would actually really like to have is a disassembly window that stayed open. Seriously? Disassembly window? I wasn't having this problem last night. Last night it would just stay open on its own. I wouldn't have to hassle it. Okay. What I would really like to have is some kind of whiteboard where I could write down these values. And I might actually use Atom as just like a scratch space to do that with. Let's fill these in. Let's take a look at our call stack. Did I not hit run? Here we are. Okay, so we're about to call sender. So let's take a look. Where am I? Wait, does this look different to you? Result equals channel. Wait. This is weird. Let result equal channel send, let result equal channel send. I mean, this is probably, I might just be psyching myself out. This is probably just the compiler. There's only one actual call to send, so whatever. What I'm looking for is this breakpoint. Go to disassembly. Okay. There it is. Oh. Okay. It just wasn't appearing here for some reason. Very mysterious. All right, so let's step into call and start seeing let's see where we are. So that's not what I wanted. That is on the wrong screen. Oh wait, hold on. I know how to do this. Okay. So source window is actually kind of useless to me. All I can really work with is the disassembly while I'm in here, and so that is exactly what I'm going to do. I'm also going to, I don't know how to work Visual Studio well enough, so I'm just going to leave these open. So we're going to use this as some scratch space. Ooh, we got some nice stuff in Windows 10. I like that. I like being able to just drag these windows around. Okay, so we're starting with copy. We know that the value on the stack's not getting corrupted, so that is not what I'm terribly worried about. What I care about is ESP and void ** ESP. We know that our starting value is 066B F554. Oopsie, I don't want to save that. That is our return address. Next up, so now let's just step through and see where ESP goes. Stop it, you. We've already changed it a little bit. So Mauve. Let's take a look at what Mauve does, because I don't understand my assembly. If Mauve is actually changing the stack pointer, I'm screwed, because it's going to do a ton of stuff. I thought Mauve was not doing that. Because if you notice within the function, it's a ton of move instructions. So let's find out what that's doing. x86 mov. Just straight up mov. Specify simple offset relative to a segment base. Copies the second operand to the first operand. The source operand can be an immediate value, general purpose register, segment register, or memory location. The destination register can be general purpose, segment register, or memory location. But that should not be... Oh, you know what? I think I'm a dumb... The reason why the value changes is because we push EBP at the beginning. I'm a doof. Push EBP. Yes, I am a doofy doof. So let's take a look at this. And we should see that the difference between the two is a difference of 4 bytes. Exactly what we'd expect because it's pushing 32-bit system, pushing like a word size, which is 4 bytes. So now let's step through and just keep an eye out for whenever that stack pointer changes. So we push EBX, push EDI, push ESI. So that actually already looks like it's potentially could be part of what's going on, because we push EBX, push EDI, push ESI. We don't pop those at the end. So we'll keep an eye out for that. Push EBX, copy value, push. So next up, let's push EDI, push EDI, copy value, push ESI. Let's F10 that junk, copy that. And let's take a look at what's going on. So we'll see that, value goes down by 4, it goes down by 4, goes down by 4, goes down by 4. Each one of these, each time these 4 bytes is pushed on the stack, which is cool. That's like, hey, look at me, I've done stuffy stuff before. Sub ESP 75C. Does that number look familiar to you? Was 75C the value that ESP was off by when we got to the end? That is something. Sub ESP 75C. And now ESP is, so it just chopped a bunch off of ESP. And now we do F10 after a call to another function. It changed again. It changed by like 4 bytes. What is going on? I honestly can't tell if all this stuff is like sensible. Oh wait, here we go. Pop EAX. Oh my god. So what we are witnessing, folks, what we are seeing now with our specialize is before we called the function, we were here. After we called the function, we were at the same spot. But we had to pop a value off the stack. What value do we pop off the stack? That's the return value. Pop EAX is getting the return value off of the stack. That's cool. That's fun stuff. So now let's go. Now we should not see that register change very much at all for a while, because none of these instructions should touch that register. But we do have call memcopy, but that doesn't touch anything. Makes sense, memcopy isn't returning a value. No changes to the register, no changes to the register. Oh, did you see something change? I saw something change. But the value is the same, so who cares? Oopsie, my morning alarm is going off. That's fine, because I don't have to do anything for like half an hour. We're going to call memcopy again, but no changes. And now it just changed again, and but it didn't actually change, so I don't know what's going on. So now we're calling another function. We are calling innermute. We're calling innermute. So let's see what happens. No changes to our stack address. Okay. Move a value. Now we jump. No jump. Move. Sub. Move. JA. And now we're back. Now we're at our end. So we add OCH. Add ESP OC. Copy value. And now we're going to F10 pop EBP. Pop EBP. And where are we? We're just nowhere near where we should be. And if we do this again, if we do expected, or we do 66B, 66BF. So if we do expected minus actual, so let's do this. You jerky jerk. Ugh, when Visual Studio, you're killing me. Turns out I have to actually do a thing. So what was that value that I thought? 075C. That is exactly it. The value that we're off by is 075C. And somehow right in the middle, it's doing 075C. So what is that value in hex? OX75C. $1884. 1.8 kilobytes off the stack. And if I just, let's restart. Let's start from the top. Reset all of our breakpoints. Let's go to disassembly. And let's run. Let's F11, and let's step. And let's just step right on over. Actually, instead of stepping over, what we can do is we can move the next execution, the next instruction that's going to be executed, just over it. So now we just don't even run this instruction. Let's just run. And now we've run right back to ret, and let's F10. what the heck is going on? This really, like, it feels to me like this is a code gen bug. Because this instruction, to me, right now, just looks wrong. I don't know if it is, like, this, maybe this is important. I don't know if the problem is this is an unnecessary instruction that's being added, or maybe this is wrong. Maybe when we add ESP at the end, maybe this should be, add 7.5C instead of add C. Oh my God, that is absolutely crazy. And the even crazier part is I don't know how to ask. Like, I don't know how I would go on the IRC channel and be like, I've got an issue where the stack pointer is being modified in an invalid way by a call to sender send. What is going on? I mean, I think I'm gonna do that, but I'm gonna have to do that offline because, oh my God, that is a crazy thing. Yeah, my suspicion is that this is either not my fault, or if it is my fault, there's still something really weird going on. Like I'm doing something that's just so obtuse and out of left field that it's just not immediately obvious what's going on. Okay, just to summarize, I was taking a look at we followed the actual addresses, all of the changes to that one particular register, the ESP register. We followed all of the ways that it was modified. At the beginning of the function, and then all the way to the end of the function. And OX 7.5C. Dun. So we followed all the ways it was doing. Prelude to the function, we call into the function, pop a bunch of values onto the stack. That's pretty common. Basically restoring the previous, like saving the previous function state or something. I don't know. Then we inexplicably pull over. Oh, so okay. So here's a thought. Subtracting 75C. When you subtract values from the stack, you're basically allocating space from the stack. We could see this with the push calls. Push adds a value to the stack, which basically adds more data to the stack. It grows the stack. And we can see that the value of the stack pointer decreased each time. So decreasing the stack pointer allocates space on the stack. So what this call is doing is actually think semicolons are the instruction or the comment character for x86 assembly. I don't know. Allocate 1884, was it? It was some number that sounded like a year. 1884. Allocate 1884 bytes on the stack. Okay, so that makes sense to me. This is doing a bunch of junk, moving things around, temporary values. So it makes sense that it's allocating a bunch of space on the stack at the beginning. What's wrong is, hold on, this is actually the wrong one because I'm a doof. Break. That's not what this was. So this was just this was adding OC. So what this looks like to me is this is allocating a bunch of space on the stack. This adding that value back to ESP should be deallocating that space on the stack. and it's doing the wrong value. Instead of OC, it should be adding 75C, the same value removed. Instead, it's adding OC, which is wrong. So that really looks like a code gen bug to me. But I'm gonna have to talk on, just basically go on the Rust forums and be like, hey, I got this weird mysterious thing going on. Can anybody potentially help me figure it out? That was exciting. I don't get to do a ton of debugging. Debugging assembly is very scary. It's like some serious esoteric dark magic type of stuff. It feels really good when you debug it successfully, but I could have just as easily gone in there and, spent an hour stepping through assembly and gotten nothing out of it. So I'm glad that I at least was able to track down what's going on, even if I don't necessarily know why it is happening. But I think that's where I'm going to call it for today. I'm not really going to be able to make any progress until this bug is resolved. So I will see if anybody within the Rust community can help me figure this out in time for me to, start streaming again within the next day or two. Thanks for watching. Thanks for sitting through my super exciting, basically disassembly debugging session. Hopefully we'll get back to actual game development or game engine development sometime soon. I promise this whole sending data through the channel is pretty cool in concept, allows us to do a lot of really parallelized resource loading, but we will get back to that sometime soon. Thanks again for watching, and I will see you all next time.